All right, so this is the second half of 5.1, but let me run through real quickly what you will see when you go back and watch 5.1 if you haven't already, the first half. So we talk about integers. Integers are positive and negative whole numbers. And we talk about how we add them together. And so there's the chip model. So in the chip model, you have these chips that I've just passed around. There's one side that's yellow and one side that's red. The yellow side are positive numbers. The red side are negative numbers. All good? Okay. No? The yellow side are positive numbers. So if you have a yellow one up in your hand like that, this would be positive 1. Okay? And if you have a red up in your hand, this is a negative 1. So if you have, in this case, the positive 5, yes, that'll work. Positive 5, it would mean you'd have 5 yellow chips. So set up 5 yellow chips in front of you. And you'd have 3 negative chips, 3 red chips. So visually speaking, you should have, let me get my buttons going here. So you have 3 red chips and you have 5 yellow chips. That's not too bad. Okay, so everybody have this like array or this like, I don't know what word I want to use. This collection, we'll call it a collection. Does they have this collection of things on your desk? Okay, RJ, here's some of these right here. Go ahead and grab a few of those out. You're welcome to pull desks over if you need more space because I realize these desks are very small. So this is what we'd look like. And then what happens is we group things together and say, hey, you know what? If I have a red one and a yellow one, because since it's a positive and a negative, we call that a zero pair, and they kind of cancel each other out. And I do this for every red-yellow pair I can do. So those two are grouped together, and these two are grouped together. And once I sort of pair them up, I figure out how many I'm left with, and this one gives me 2 that I'm left with, 2 yellows. So this is the number 2 because yellow chips are positives. Okay, this is a chip model. The charged field model is very similar, except that we use pluses and minuses. So when you see the 5, you use 5 pluses, and you see the 3 as negative, you use 3 minuses, and you zero pair them up as well. And I'll let you see that later. And then there's the number line model, and the number line model works like this. And it's again, this is a really good one for your kinesthetic learners. So Macy, we're going to call your row 0, okay? Okay. All right. So if I start here, and it says I'm going 5, I'm going to go 5 rows over. So you can talk about going here's 1, and here's 2, and here's 3, and here's 4, and here's 5. And then negative 3 means I'm going to go back that way 3. So I'm going to go 1, and then 2, and then 3. And I look at how far I was from the row I started with, and the answer would be 2, right, Macy? I'm 2 rows away from where you were. Does this sound like what the video already explained, Jazzy? Oh, this is good news. All right, good deal. So when you listen to this again, it will sound somewhat familiar. So number lines are really great because kids can get up and move around. You could put things on the floor. It doesn't have to be desks. I'm using desks because I don't have any tape on the floor. You can put tape on the floor. It works really well to sort of have this idea of moving forward and backward. Pattern model, definitely my least favorite model, but I will say those of your students who maybe have like Asperger's or autism, this can be something that really resonates really well because patterns work really well sometimes for some of our students. And so the idea for this one, I'm going to actually write this one out because it is a little bit different, is to take something that we can actually work with that we already know, like 5 plus 2. It's positive numbers. 5 plus 2 is 7. And then we do, okay, for 5 plus 1, I know that one as well because it's positive numbers, it's 6. And then 5 plus 0 would be 5. So we establish a pattern using numbers that we already know something about, namely the whole numbers, right? And then we continue the pattern by decreasing that term in the middle each time. So this is 5 plus negative 1, 5 plus negative 2, and then I have 5 plus negative 3. And what will happen is that the pattern that was established on the right-hand side continues. It went 7, 6, 5. It goes 4, 3, 2. So down here at the bottom, we also have yet another way of showing that 5 and negative 3 add together to be 2. Okay? So these are the different methods that we have. This talks about absolute value. Absolute value is the distance away from 0, how far away you are. Distances are always positive. Okay, so we always are looking at something that is positive. It always feels a little bit funny to write it this way. This says the absolute value is a negative, but that's not really what it says. Notice this condition over here says that x is a negative number. So if x is a negative number and you put a negative in front of a negative number, what happens? You get a positive. So we do not have a way in mathematics to say, take away the negative. So what we do when we want to take away the negative is we just put another negative on there. Because a negative and a negative right there beside each other means opposite of a negative number would be a positive number. So this expression in yellow or in orange is not saying that the number is negative. It's saying it's the opposite of a negative number, which gives me a positive value. All right, I'll let you look at those later. Let's actually look at Theorem 5.2. This is a good place, I think, for us to start Theorem 5.2, and then we'll move into subtraction. Okay, so the additive inverse property introduces the idea of having an inverse. So this works because we're working with integers now. Whole numbers did not have this property. This actually says that for every value, there is a negative, or for every negative value, there's a positive, so that when you add them together, you get 0. So if we have 5, that number would be negative 5. If we have negative 7, that number would be positive 7. There's always a negative and a positive pair. They pair up, and they add to 0. Okay, that's what this additive inverse property says. And this talks about what happens when we have positives and negatives and being multiplied and so forth. In particular, that first one we've already talked about. If you have the opposite of a negative, you get a positive. So negative times negative a is just a. If a is equal to b and you add a number to it, it doesn't change it. I talk about this one a lot of times in terms of like if Harley were to stand up here next to me, I think you're probably taller than me, Harley, because I'm pretty short. So if Harley and I were standing here next to each other, and let's just say for the moment that we were the same height, right? And we both then took a step up on top of the chairs, and we're both standing on the chairs, because the chairs are the same amount of height, we would still be the same height. So if you take two numbers that are equal and you increase them both by the same amount, they're going to still be equal. That's what the second one is. The third one talks about what happens if you add negatives together. This is one of the places where kids get really frustrated because of properties of integers really trip kids up. So this is looking at like 6th to 7th grade, right? Looking at integers like this, by the way. So when you have a negative a and a negative b, we're gonna need the tiles again. So you guys putting them away is not helpful right now. So hold tight. I'm sorry. We're going to have a chip model for subtraction in just a second. I'm so sorry. I should have said that. So just hold tight to them. Stick them on the desk next to you if you want them out of the way. All right. So if you have a negative a and a negative b, you just add the a and the b values together, and the whole result is negative. So a and b added, and then a negative in front. Okay? All right. Integer subtraction. So for any integers, a and b, a minus b is the unique integer n such that a is equal to b plus n. So in other words, if we have a minus b, it's going to be equal to n only if a is the same as b plus n. That's the statement sort of written on top of each other. And you know this to be true, right? Like if you do 6 minus 2, what is 6 minus 2? 4. I'm not asking a trick question, I promise. The reason is because 2 plus 4 is equal to 6. And we call them fact families. That's what you usually hear them called linguistically these days. These are called fact families. And the last theorem before we do our models, where we're going to use our chips here in just a second again, says that if we have a minus b, it's the same thing as a plus negative b. I have a very distinct memory. Maybe I've already said this in this class. I can't remember because I said it recently in some class. Of a 7th grade math teacher saying there's no such thing as subtraction. Have I said this in here? No. Excellent. It was a different class. There's no such thing as subtraction. She said it lots of times in my 7th grade math class because she would each say, always, it's just adding a negative. Right? There's no such thing as subtraction. It's adding a negative. And that's what this is saying. The same thing as adding a negative is the same thing as subtracting. They're different perspectives of it, but they're equal to one another. All right, you ready to do the chip model? Okay, if you don't have chips, grab some. You need some. Okay, I'm going to do it on here visually, but I want you to do it with the actual chips because that's what you would do with your kids if you were working with this model. So this says that you're going to need 5 chips. So I need you to get 5 yellow chips out. Okay? So you should have 5 yellow chips in front of you. On your page, it should look something like this. Got 5 yellow chips. Do you have 5 yellow chips? Wonderful. Now, here's the deal. This negative is the negative you guys wanted to always use when we talked about subtraction. The one that we thought about is take away. Everybody good? We're going to take away. But it says we're going to take away -3. Negative is red chips. I'm supposed to take away red chips. How many? 3. Now, if you look at my picture, and if you look at what you have on your desk, there are no red chips to take away. All I have are yellow chips, right? Okay, so here's what you do. You take a red and a yellow, 0 pair, and you put them on the desk for yourself now. And you do it again, a red and a yellow, 0 pair, and you put them on the desk. And you do it one more time, a red and a yellow, 0 pair, and you put them on the desk. So in pairs, you're putting in a red and a yellow, and this is what's on your desk right now. Okay, is this what everybody has on your desk? Okay. This number is still 5. Because these 0 pairs cancel one another out. The number in my circle is still 5. Okay? It looks funny, but its result, if I were to simplify it, is the number 5. The reason we want those in there, though, is because now I have an image where I can take 3 red chips away. Do you have 3 chips that are red that you can take away now? Yeah, you do. So you're going to take them away. 1 out, 2 out, 3 out. So I can take my 3 red chips away. What do you have left? What do you have?
8.
You have 8 yellow chips. I think that's 8. This is the number 8. What does this do for us? Well, what it does in a visual way is it justifies what you wanted to do probably from the beginning. From the beginning, what you wanted to probably do is this, did you not? You wanted to say negative times negative, I can change it both to positive and I will get an 8, and I know that that's going to give me the right answer. And you know that because you've done work with integers for probably better part of 6 or 7 years, right? You know this because you've done it over and over and over again. But you may not have really understood why you did it. And this is a picture with chips of why it works. I put things in 0 pairs, and then I remove the negatives out. I removed out the negatives. I'm left with 8 positives. This is the number 8. Okay. I can do the same thing with my charged fields model. Now, if you haven't watched the video, you haven't seen the charged fields model. That's okay. You'll watch it later, but I'm going to show it to you from the subtraction perspective. So in my charged fields model, I'm supposed to have 5 positives, just like I had the 5 yellow chips. This says that I need to take away 3 negatives. Well, there are no negatives to take away. So I put them in 0 pairs. I put in a positive and negative, another positive and negative, and another positive and negative. This circle still has the value 5. Okay? But it's expressed in a way that I can remove the 3 negatives now. So I can take each of these negatives and take them out, and it will leave me with what? 8 positives. Okay, charged field model and chip model, they're the same model. They're just visually different. Okay, they look a little different visually. One of them has the really nice chips, that actual physical chips that you can use. This one sort of has positive and negative charges, which also sometimes sort of resonate with us a little bit differently. So they might actually make more sense depending on the child you're working with. Another option. All right, we need to talk about number lines though. Number lines really fun. Okay, so I'm going to draw it on the paper, and then I'm going to move around my desks, okay? So let me draw it first, and then we'll talk about what it looks like when we move. Okay, so here's our number line. We start at 0. And this one says I move forward 5. So here's where I am. So in some sense, I can jump them individually, but I've moved from 0 to 5. Are we good? Okay. And then what's going to happen, I'm going to draw it, and then I'm going to show it to you actually, let me show it to you first, because I think it might make more sense. Okay. So we're going to start over here with Macy again. Row 0. We're going to move forward 5. So I have 1, 2, 3, 4, 5. I needed to have started before Macy, but it'll be okay. Then the first negative tells me that I turn around. The second negative tells me I'm going to walk backwards. 1, 2. Right now I'm not going to jump out the window, but I need to move one more beyond my window, right? Yeah, I do. And how far am I away from Macy if I do that? I'm going to be 8 away. So that somehow I have to indicate that I've turned around, and then I'm going backwards 3 more. Those don't look good. How about there? I've moved backwards 3 more over here, and I'm now at 8. So the first negative is telling you turn around. The second negative is telling you move backwards. Okay? All right, that is the number line model. And then we're going to look at the pattern model. Okay, so the pattern model still needs to be doing something that's established with what we know to begin with. So we need to subtract 2 whole numbers that we know. And 5 minus 2 is a pretty good place to start. If you wanted to start at 5 minus 3, that's okay. But 5 minus 2 will work. So what is 5 minus 2?
3.
It is 3. And then we're going to go down. 5 minus 1 would be 4. And then 5 minus 0 would be 5. Okay? So we're going to keep going in this pattern where the 5 minuses stay the same, but I change the number on the inside. So I've gone from 2 to 1 to 0 to negative 1. And then I've got negative 2. And then I've got negative 3. So if I do 5 minus negative 1, that would be 6 if I'm continuing the pattern. 3, 4, 5, 6, 7, and 8. So down here at the end, 5 minus negative 3 would be 8 from the perspective of a pattern. All right. Last thing in this section is something that when I teach this again, I'm going to shift it because I think it fits in a little bit better from the way that they've revamped your book at different points, was order of operations. You guys have done a little bit of stuff with order of operations before, but let me talk with you again about it here. So order of operations, probably one of the acronyms that you're familiar with is PEMDAS. Please excuse my dear Aunt Sally. Sometimes people memorize it that way. P stands for parentheses. E stands for exponents. M and D are the same thing. What do they stand for, though? What is M? Multiplication, and D is division. Okay, here's the deal with multiplication and division. Multiplication and division occur at the same time, which means you don't multiply before you divide. You don't divide before you multiply. You do them at the same time, moving from left to right. So this is multiplication, division. And I want you to write yourself a note in. It's from left to right. So if division occurs before multiplication as you move from left to right, you're going to do division first. And the same thing occurs with the A and the S. This is addition and subtraction. So add, subtract. And it is, again, from left to right. So if addition occurs first from left to right, you do addition first. But if subtraction occurs first from left to right, you're going to subtract first. There is not an ordering of this. So while we say PEMDAS, we could say PEDMOS or PEDMSA. It doesn't work very well, right? Like PEMDAS works nicely because it flows, which is why people do it the way that they do it. It's not because the addition and subtraction have a natural ordering to them among themselves or the multiplication division. So when we're looking at this, for example, which of these are we going to do first? Well, we're going to go through our steps. There's no parentheses, so I don't have any parentheses. There's no exponents, so I don't have any exponents. Multiplication and division is next. So what do you see that we will do first in terms of multiplication and division? Division, yeah. The 6 divided by 2 comes first if I move from left to right. So I'm going to very carefully write out, what is 6 divided by 2? 3. What would I do next? The multiplication, yeah, the 3 times 4, which would give me 12. What would I do next? Well, multiplication, division, they're all done. So now we're in the addition and subtraction. What would I do first? Yeah, I would be subtracting first. So 5 minus 2 would be 3. And then I'd have 3 plus 12, which would be 15. Order of operations are really important. And the reason it's really important is because if I do a problem and RJ does a problem and Sarah does a problem and Macy does a problem, we want to all get the same answer. I mean, right? Like that seems like a reasonable desire that we do the same problem, we get the same answer. But that means there needs to be an order in which we do it that we all agree to. This is the order that has been agreed to. Make sense? All right.